Okay, so we're going to start with chapter 9, which deals with the important concept of bonding. I need to back this up. Okay, so yes, in this chapter, we'll be looking at chemical bonding, all right? And basically, what we're concerned with in this particular topic is how atoms and ions are held together in compounds, all right? So just to give a bit of a preview, that's what bonding is all about. It's talking about the forces that would hold atoms and ions together in compounds. So in the case of molecules, there's one type of bonding, and in the case of ionic compounds, there is another type of bonding. All forms of bonds are electrostatic forces. Basically, what that means is that these forces occur between positively and negatively charged particles, right? So it doesn't matter if you're dealing with ionic bonds, which we're going to talk about shortly, or molecular bonds or covalent bonds. The basis of them would be electrostatic in terms of the attractive forces between opposite charges, all right? So just to give you a very simplified version of what we're talking about here. So what we're talking about here, or what I'm showing you here, is a model representing two hydrogen atoms held together by some forces, collective forces, all right? The top one shows you what happens when you have two hydrogen atoms, which each has a proton present, and you have an electron. So basically, it's an ion that is formed between the collection of particles here, right? So what you can see here is that there'll be several forces at play because you're going to have repulsive forces between the positively charged particles, and you're going to have attractive forces between the proton and the electron that is being shared between the two atoms, all right? The bottom one is what actually exists in nature, where you have two protons, right, sharing two electrons. And again, you have some forces at work here. You have repulsive forces between like charges, and you have attractive forces between unlike charges, all right? So that's basically what's happening. So the question now becomes, what would be the net effect, all right? And the answer is that it depends on, among other things I should add, the distance between the nuclei. And what you're going to find is that for most molecules, there will be a stable arrangement where the distance between the nuclei would be of a certain value, all right? So again, going back to the hydrogen example, this is showing you how the energy of the molecule varies with the distance between the two nuclei, all right? In the case of the hydrogen molecule. And when it comes to these things, of course, in science, we try to use models to explain what we observe. And one model that has been used, even though it's not 100% accurate, but it works in some cases, it's a model of, if you can imagine, a spring, and at the end of both springs, you have two metal balls, right? So basically, the metal balls represent the atoms, and the spring represents a bond between them, all right? So what happens when you force the two atoms close to each other? The energy is increased because you're going to have some resistance that's occurring between the two particles. And the reason why the resistance occurs is because the two particles are positively charged. The two nuclei are positively charged. So therefore, that is what's happening here, right? The energy will increase, all right? And that's because of the net repulsion that would take place between the two nuclei, which are positively charged.
So the closer they get, the more they want to repel?
Exactly, right, exactly. And in fact, there's a formula. In fact, I was just looking at it in your textbook. If I can, let me see if I can bring it, if I can find it. There's a formula that I came across. You don't really need to know it, but this formula shows you what you just asked. Oh gosh, where is it? Where is it? I just saw it not more than 15 minutes ago. Oh, here it is, right here. The enthalpy of the, well, this is relation to ionic compounds, but it could relate to what we just talked about. Basically, the smaller the distance, the greater would be the energy, right? So the formula, this is for an ionic compound, but it applies to also the model that we're using, right? Basically, there's an inverse relationship between the energy and the distance. So the closer you bring them together, the energy of the system, in this case, the H2 molecule, increases, all right?
Distance and energy are inversely related.
Right, exactly. So going back to the PowerPoint, so that's what happens when you are pushing the atoms closer to each other. Now, on the other hand, when you try to pull them away from each other, there will be another attractive force. Well, there will be a force, which will be a force of attraction that exists between the electrons that are shared and the protons in the nucleus. So therefore, that force would increase until you get to a breaking point where the bond breaks. And when that happens, then there's little to no force of attraction that exists between the particles, all right? So that represents, going back to the spring and metal ball model, that represents basically where the spring breaks, right? So therefore, that represents the bond breaking, and therefore there's no attractive force that exists between the particles, all right? So when the nuclei are pulled far apart, then there'll be little or no attraction between them, all right? Now, as they get closer, then basically the attraction increases, and then you get to a minimum point here, right? Where the net attractive forces will be equal to the net repulsive forces, right? And therefore, at that point, the energy is at a minimum. So in the case of the hydrogen molecule, the distance between the two nuclei at that point would be 74 picometers, all right? And the energy that would be required to break that bond would be minus 436 kilojoules, because this axis here represents zero energy, and this here is minus 436 kilojoules per mole. So therefore, if you want to go from here to where the bond is completely broken, you're going to need to supply this amount of energy in order to achieve that. And then as you bring the nuclei closer to each other, then as I said before, the energy starts to increase because of increased repulsion between the two charges. Okay, so that is basically a very simplified version of explaining how bonds work in terms of the most stable structure, all right? Now, when it comes to bonding, our main concern is the number of valence electrons on the atoms for the different elements, because the valence electrons are basically what plays a very fundamental role in chemical bonding. Now, in the case of a combination of metal and nonmetals, when they chemically combine, what happens is that the electrons would leave the valence shell of the metals and enter into the valence shell of the nonmetals. The result of that is that the metal atoms will be converted to metal ions, and the nonmetal atoms will be converted to anions. So the metals will be converted to cations, the nonmetals will be converted to ions, and these particles will have charges, and therefore they will be attracted to each other. And that force of attraction between ions of opposite charges, we call those forces ionic bonds, all right? In the case of combining two nonmetals, what will happen is that you'll have sharing of electrons between nonmetallic atoms as far as their valence electrons are concerned. And as a result, you're going to end up with what are called covalent bonds. And these covalent bonds are the result of the attraction between the nuclei of the different atoms and the shared electrons, right? In either case, in the case of ionic bonding or covalent bonding, what you'll find is that the atoms themselves will either lose, gain, or share electrons to end up with a noble gas configuration. Now, let me just say here that this is true for sure when it comes to most representative elements, meaning the A group elements. This would not be true for transition elements. Things are a bit more complicated when it comes to explaining how many electrons are being lost or gained in the case of transition elements like iron, like manganese, like cobalt, and so on, all right? But when it comes to elements in groups 1A through 7A, well, not 7A because they don't form compounds, 1A through 6A, they tend to form compounds such that the resulting ions or atoms, if it's a molecule, will end up with an octet or basically a noble gas configuration. All right? Yeah.
So when gases or when atoms bond together,
Hmm.
they aim for that noble gas configuration of the 8 valence electrons. Is that why it's so difficult to bond any of the noble gases with anything?
Yes, exactly. Because the noble gas, right? The noble gas elements already have their full complement of valence electrons, right? Helium has a maximum of 2 because there's only one shell in the case of helium.
Right. 'Cause
But
it's super.
exactly. So in the case of the other elements below helium, they would have 8 electrons. So therefore, they have very little tendency to form compounds. In fact, as far as I know, I need to check up on this, but as far as I know, nobody has successfully made a compound with either helium or neon, right? Nobody has succeeded in doing that. Now, for the other elements below them, like xenon and so on, people have been successful in making compounds with those elements. But even then, they have to employ, some really stringent conditions in order to first make them and also to keep them. Because if you make them and then you just leave it, like on this table here in the regular environment, it will just break down to form back the original group 8 elements. So those elements, they definitely don't participate in a lot of reactions.
Does neon have any use at that point? I mean,
Well, I mean, I think, well, I know neon has been used in not for chemical reactions, but in the neon lights, right? That's usually neon gas under low pressure in a lamp. When you hook it up to an electric circuit and you perform a discharge, it glows, right? Right, exactly. But in terms of chemical reactions, as far as I know, there's no usage as far as neon is concerned, and the same is true for helium. Okay, so let's talk about Lewis symbols. Lewis symbols is basically a way of representing an atom indicating the number of valence electrons. And it's a very simple idea. Basically, all you're going to do is write down the formula for the particular element, and then you use dots to represent the valence electrons, right? So I think I have some examples here.
It's like a Lewis.
Like here.
Lewis. Okay, no, never mind.
Right? So for example, in the case of lithium, 1 dot, right, with the symbol. In the case of beryllium, 2 dots, and so on and so forth. That's basically it, right? Now, in some textbooks, they are very particular in terms of how you arrange the dots. So as stated here, in writing the Lewis symbols, the first 4 dots are placed singly on each of the 4 sides of the chemical symbols, and then you pair them up if you need to add more electrons. Me personally, I'm not a stickler for that, right? You can pair them up as far as I'm concerned, or you can put them singly, all right? And it says here, Lewis symbols are used primarily for those elements that acquire the noble gas configurations when they form bonds, as I said before, all right? So that's basically what Lewis symbols are all about. Now, later on, we're going to learn about Lewis structures when it comes to molecules and polyatomic ions, right? And it's related to what we just discussed here. But as far as Lewis symbols for elements are concerned, this is it, right? Nothing too complicated. So if you want to write down a Lewis symbol for a particular element, what you'd have to do is go to the periodic table, you look up the symbol for the element, and you look at the group number, and then you put the number of dots equivalent to the group number around the symbol, and that's it, all right? Okay, so that's all I'm going to say about that. So here's a simple example. Give Lewis symbols for magnesium, silicon, and phosphorus. So in the case of magnesium, we put Mg, and then you go to the periodic table, and you look up the group number of magnesium, and it's 2, so you just put 2 dots, and that's it. In the case of silicon, the symbol is Si, and if you go to the periodic table, you see that silicon is in group 4, so you just put 4 dots around it. And then finally, in the case of phosphorus, you put the symbol P. Phosphorus is in group 5, so you put 5 dots around it. 1, 2, 3, 4, 5, and that's it. All right, so that's basically how you would write down the Lewis symbol for particular elements, all right? Okay, so let's talk about ionic bonding, and then we're going to talk about covalent bonding. Now, in the case of ionic bonding, again, we're looking at the valence electrons. And basically, as I said before, in the case of the formation of ions, you have electrons leaving the metallic atom and transferred to the non-metallic atom, and you end up with your noble gas configurations, and the ions that are formed are held together by strong electrostatic forces, right? So let's see here. It says when atoms lose or gain electrons, they may acquire noble gas configuration, but do not become. Oh, right. So that's what I just said. They will end up with the noble gas configuration, but please note that they're not the same as the noble gases because they'll have different numbers of protons, even though the number of electrons will be the same and the electron distribution would be the same. However, or not however, but continuing. The two ions formed will be strongly attracted to each other. I said that before, and will form an ion pair. And therefore, the net attractive force between the ions would be what we call the ionic bond. And as a result of that, the resulting structure, gross structure of the compound would be basically an arrangement, a highly ordered arrangement of ions, and that is called an ionic crystal, right? So basically, there's no such thing as a molecule when it comes to the formation of ionic compounds. Here's an example of this, sodium chloride. Now, if you take a small piece of sodium metal and drop it into this flask, which contains chlorine, you're going to get a very explosive exothermic reaction, right? Generates a lot of heat and a lot of light, right? So the reaction will continue, and then when the reaction is complete and everything cools down and you look at the bottom of the flask, you're going to see crystals of sodium chloride, right? And this is the same sodium chloride that we consume in our foods, which is common salt, right? Now, what you'll find is that if you were to look closely at the actual structure at the microscopic level, you're going to see something looking like this, a highly ordered arrangement of positive and negative ions, all right? There will not be any discrete molecules of sodium chloride. This is what you'll observe, right? And basically, the ratio in this case of sodium to chloride ions would be 1:1, right? And different compounds, different ionic compounds will have different arrangements, right? In fact, I'm hoping, I don't know if we'll get to this later on, I'm hoping that we'll get to the chapter dealing with, looking at crystal structures in more detail, and you're going to see that in some compounds, and it's related to the ionic sizes, right? In some ionic compounds, the arrangement will be different from others as a result, all right? So this is basically the arrangement in the case of sodium chloride, and this is basically what you'll observe pretty much for all crystalline ionic compounds, all right? So, of course, sodium being the metal atoms will donate electrons to the chlorine atoms in the chlorine molecule, and the result will be the formation of the sodium and chloride ions. These ions are oppositely charged and therefore will attract each other and assemble themselves into a highly ordered arrangement, as you can see here, all right? If we were to use Lewis symbols to represent what happens in ionic bonding, basically, it would look something like this, right? So you have the sodium atom with its single electron, right? And you have the chlorine atom, which has 7 electrons on its outer shell. So what's going to happen? The sodium will donate its single electron to the chlorine, and therefore you're going to end up with the sodium ion and the chloride ion. Sodium ion is positively charged, the chloride ion is negatively charged. And again, as I said before, the attraction between those ions results in your ionic compound. And let me just say, and I probably should have said this when I showed you this here, because of the strong electrostatic forces that exist between the ions, the result of this is that sodium chloride, like any other ionic compounds, will have a high melting point, high boiling point, and will be hard, right? Those are just some of the properties that will be observed when it comes to ionic compounds. They tend to be hard, right? They tend to have high melting points, and they tend to have high boiling points, all right? And that is all as a result of the strong attractive forces that exist between the ions, all right? Okay, so let's move on to an example here which says, use Lewis symbols to show the formation of ionic bonds between the magnesium and nitrogen. What are the name and formula of the compound that results? Well, we can do the first part, or I should say we can do the second part first. The compound formed between magnesium and nitrogen would be magnesium nitride. The formula would be Mg3N2. Magnesium. And we all know how to do that already. I won't go through that right now. So to do the Lewis symbols representation of what happens, magnesium is in group 2, so it has 2 electrons, and there are 3 of them, right? And the nitrogen, there are 2 of them, and each nitrogen atom will have 5 electrons, right? So what's going to happen is that this electron here from the magnesium will transfer to this nitrogen. This electron will transfer to the same nitrogen. And then this electron will transfer to the same nitrogen. And then this electron will transfer to this nitrogen. And this electron and this electron will transfer to the other nitrogen. So the result of that would be Mg2 plus being formed, 3 of them. And the nitride, there are 2 of them that would be formed as well. 3 minus, 3 minus, and that's it. All right? And that's basically what the question is asking for. All right? Okay, any questions about this? Any questions? Any questions? All right, continuing. Okay, now, unfortunately, I forgot to print the handout for this chapter. So, unfortunately, I'm just going to teach, and then next class, I'm going to bring the assignment so that we can work on that one together, right? Because based on what we have covered so far, I think there are some questions in that assignment that we could do. But anyway, so let us talk about the type of energy changes that would take place when an ionic compound is formed from its element, right? Now, one might think that, okay, if we can figure out the energy changes for the first ionization energy of, let's say, sodium and the electron affinity of the chlorine atom, then that would give us some idea as to the energy changes that would take place. It turns out that these are just 2 of other energy changes that we have to consider in order to accurately determine the energy changes overall as the elements are converted to the ionic compound, right? So, 2 guys came up with a way of looking at this, Born and Haber, right? They came up with what is called the Born-Haber cycle, all right? And this is basically a cycle that is used to explain the different changes that the original metal and non-metal start from, and it goes through several changes to get to your final ionic compound form between those 2 elements, all right? So we're going to look at one example of the Born-Haber cycle as it applies to the formation of sodium chloride from sodium and chlorine. So this is basically the Born-Haber cycle for that compound formation. And what I'm going to do is go through the different steps to show you what is happening in each step, all right? So here is sodium and chlorine, right? What we're looking at is sodium plus chlorine to form sodium chloride, okay? Now, the enthalpy of formation of that has been measured and is equal to minus 411 kilojoules, all right? What we're going to look at is the different changes going this way to determine, to see how these values here relate to this, right? Now, let me just say from the outset, because of Hess's law, right? If you remember what Hess's law says, Hess's law says that it doesn't matter the route that you take to go from reactant to product, the enthalpy change is going to be the same, right? And that is no less true here. It doesn't matter if you go directly from here to here or go through these different steps to end up with the same destination, the enthalpy change will be the same in both cases, right? All right, so with that said, let us look at starting with step 1. If you notice in step 1, the change that is taking place here is that the sodium solid is being converted to sodium gas, right? Now, we call that sublimation. I don't know if you have met that term before. Sublimation is what happens when a solid goes to the gaseous state without going through the liquid state, right? So the enthalpy that occurs when that happens, we call that the enthalpy of sublimation. So I'm just going to put sublimation here. All right. So that's the energy change that takes place when the sodium solid is converted to sodium gas. All right. So that's step one. Step two is where the chlorine molecule is converted to chlorine atoms, right? So basically, you're converting the molecules to atoms. We call that atomization. All right. And the amount of energy needed for that is 122 kilojoules, right? Okay, so that's step two. Step three is where the sodium gaseous atom forms the sodium gaseous ion by the loss of an electron. And this is something that we met before, right? If you remember, we talked about what do you call it? I forgot the term. Ionization, where basically the sodium gas, right, in a gaseous state is converted to the ion by the loss of electrons. So this is basically enthalpy of ionization. Enthalpy of ionization, all right? And then the next step is where the chlorine gas atoms gets the electron to form the chloride ions, right? So this is called electron affinity, something that we met already as well, right? And then the last step, and let me just say, again, this is one of those situations where different sources, textbooks and so on, have different interpretations. The last step is where the sodium ions and the gaseous ions react to form your sodium chloride, right? And the enthalpy change for this is minus 787. Now, in some textbooks, they call this enthalpy change here the lattice energy, as it is shown in this slide right here. However, in your textbook, and I'm going to show you exactly the page, they consider the reverse to be the energy change for the reverse. That would be the lattice energy. So if you go to your textbook, and I was looking at it this morning just to see what it says, right? According to your textbook, the definition of the lattice energy is the energy required to break up your ionic compounds into its constituent ions. In other textbooks, they say that the lattice energy is for the reverse reaction, right? So what I'm going to do, since your textbook says that, I'm going to use the textbook definition, all right? Even though in other textbooks, you'll see something different, right? So, I'm sorry, yes, sir.
Couldn't it be true for both? It just depends whether it's positive or negative.
Exactly, yeah. But I mean, in terms of the actual definition, some textbook, like this textbook says it's for the breaking up,
Okay.
right? But you're right. The reverse would be the negative of,
Like
what
negative lattice energy means
exactly. But in some textbooks, what you just said would be considered the lattice energy, not the negative.
Okay.
You see what I'm saying? So that's what I'm saying. I'm just trying to make sure you understand what's happening. So because your textbook says it this way, I'm going to stick to that definition, which means that going back to the PowerPoint here, let me show you here, which means that according to your textbook definition, the lattice energy would be the energy for the reverse. Okay, what's going on with this here? Okay, would be for the reverse, which means that it would be plus 787 kilojoules, all right? So basically, most of the problems that you're going to encounter when it comes to Born-Haber cycles is to find the lattice energy. And the reason why is because the lattice energy is seen as a reflection of the stability of the ionic compound. In other words, the greater the lattice energy, the more stable the ionic compound. So basically, let me just scratch this out here just to avoid confusion. So basically, going from here to here is the same thing as going from all the way around here to this, which would mean that this would be minus 787 going in the other direction. Or another way of stating it is that going from here to here is the same thing as going from here to here, all right? So those are just different ways of showing you how to relate the different terms. But most of the problems that you're going to get, as I said before, involves calculating the lattice energy. including the problem that's in your assignment, which I forgot to bring to class. So we're going to look at that in the next class, all right? Okay, so that's a Born-Haber cycle. Okay, here's an example using a Born-Haber cycle. I'm going to need some space here, so let me get out of this here. Okay, what's going on here? Why is this not responding? Okay. Okay, let me see if I can squeeze it in down here. So the question gives you some data for magnesium fluoride. So this is the compound here, right? They gave you the enthalpy of sublimation. They gave you the first and second ionization energies. They gave you the bond dissociation energy. Oh, that's another term too. I forgot to mention. We're going to meet this term later on. Basically, the bond dissociation energy is the energy to break up the bond between two atoms in a molecule, all right? The term I used earlier was, what was the term I used earlier?
Was it ionization?
No, not ionization. The term I used for here.
Atomization.
Atomization, right. The other term, alternative term is bond dissociation energy.
What's step 4?
Step 4 is electron affinity. Right. All right. So going back to the question. So, so they gave you the first and second ionization energy. They gave you the bond dissociation energy. They gave you the electron affinity of fluorine. And they gave you the enthalpy of formation of magnesium fluoride. All right, so I think I should be able to squeeze this in here. So basically, we're going from Mg solid plus F2 gas to form MgF2 solid. All right? And this here, the enthalpy change for that would be enthalpy of formation, all right? So let's look at the different steps that each of these elements will undergo. I'm going to start off with the magnesium, right? So the magnesium will undergo sublimation. So that is delta H sublimation. And that is equal to 146 kilojoules per mole. All right. And then for F2, that's a bond dissociation energy for F2. And that is equal to, that will give you 2F here. And that is equal to, where is it? Plus 159 kilojoules. All right. So here you're going to have 2F gaseous atoms. And here you're going to have magnesium gaseous atoms, right? And then the next step is the ionization of magnesium. Now, in the case of magnesium, it's going to lose 2 electrons. So you're going to have I1 plus I2, right? The first and second ionization energies. And those values are given here and here. So what I'm going to do is add those two together to see what the total amount of energy needed to carry out that ionization. So that will be 738 plus 1451. And according to my calculation, that gives you 2,189 kilojoules, all right, per mole. Now, in the case of the fluorine, this will undergo a change where the electrons that are lost from the magnesium will be added to the fluorine. So that would be electron affinity. And 2 fluorine atoms will gain 2 electrons, so we have to multiply that value by 2. So the electron affinity is given as, right here, minus 328. So I'm going to multiply that by 2. And according to my calculation, this gives minus 656 kilojoules per mole, all right? And then now we go from here, well, we go from here to here to get the lattice energy, which is what the question is asking for, right? Because remember, I'm going by the textbook definition, right? The lattice energy would be the energy required to break up the magnesium fluoride into its gaseous atoms. So this is what the question is asking for, right? So basically, applying Hess's law, what we're saying here, oh, by the way, before I forget, delta HF is given. Where is it? Right here. So this is equal to minus 1124 kilojoules, right? Okay, so basically we have everything we need to calculate delta H lattice, all right, or lattice energy. So basically, going from here to here is the same thing as adding all of this here together. All right, so I'm going to write down delta HF. In fact, let me use the numbers instead of the symbols. So, hold on. So, delta HF, which is minus 1124 kilojoules per mole, is equal to, not equal to, I'm sorry, plus delta H lat, all right? And we set that to be equal to the sum of all of these here. So this would be 146 kilojoules per mole plus 159 kilojoules per mole plus 2189 kilojoules per mole plus minus 656 kilojoules per mole. All right? So what I'm going to do now is work out what all of this would give. So that's 146 plus 159 plus 2189 minus 656. And, okay, running out of space here. So I'm just going to continue up here. So I'm going to end up with minus 1124 kilojoules per mole plus delta H lat is equal to 1838 kilojoules per mole according to my calculation, which means that delta H lat will be equal to 1838 kilojoules per mole minus 1124 kilojoules per mole. So minus 1124. So according to my calculation, this works out to be equal to 714 kilojoules per mole. And that's it. So that would be the amount of energy needed to break up magnesium ions or magnesium fluoride into its constituent ions. And let me just say that the lattice energy is always going to be positive, right? So if you do your calculations and you end up with a negative answer, then you must have done something wrong in your calculations. All right? Okay, any questions about this example? Any questions?
The adding of the first ionization and second ionization energy. What
Right here.
is that?
So
Is that
that would be the 700, that would be the 738 here. And that would be the 1451, oops, the 1451 here.
And is that the
That would be the 2189.
right? The part of the process is that the
The what?
trying to think how I'm trying to phrase this. Is that part of the electron affinity or the transferring of the electrons, the ionization?
Ionization energy.
Oh, right, because I'm
Exactly.
okay, that makes sense. Because yeah, okay, because you're pulling the ions off of it to
Putting
give
the
us
electrons from the magnesium atoms, and the electrons will be transferred to the chlorine. And that's the reason why,
okay,
and also very important, since you mentioned it, you notice that there are two fluorine atoms here. So each fluorine is going to get an electron. So that's why we multiply by 2 here for the electron affinity.
for the bond association energy.
Well, the bond association energy was done before. I'm talking about once you get the fluorine atoms and they get electrons, right? There are 2 of them. So each fluorine atom will gain an electron, which means that the total electron affinity will be twice that amount.
Electron affinity.
That is something important you have to pay attention to. It's a very common error that students tend to make. They don't take into account the number of atoms that are involved,
Right.
right? So like in the case of the sodium chloride that I showed, there was only one chlorine atom. So therefore, the electron affinity is just whatever the value is. But if you have two or more, you have to take that into account, right? You have to multiply by 2 or 3, depending on the number of atoms involved.
And magnesium has 2 valence, that's why there's 2 fluorines.
Exactly. Magnesium has 2 valence electrons, so therefore it's going to lose 2 electrons. And therefore you have to add the ionization energy for each electron loss.
Is electron affinity kind of like the opposite of ionization?
It is actually the reverse of ionization energy. So, and yeah, another thing I want to stress, since you said that, ionization energies are always positive, electron affinities are always negative, always, right? So that's how that works out. All right. Okay, what next? All right, so let's talk about Lewis structures. So we talked about Lewis structures for atoms. Now we're going to talk about Lewis structures for molecules, right? So the Lewis structure, as you're going to see, is related to Lewis symbols, where we combine the symbols so that we end up with a structure represented which shows you the covalent bonds that exist between atoms. In most cases, the Lewis structure shows the bonded atoms with the electron gas configuration, but not true in all cases, and we're going to see some exceptions later on. But in most cases, all the atoms try to at least end up with 8 electrons on its outer shell, right? So when you get the electrons shared up, each atom may have a noble gas configuration, but as I said before, this is not always the case, all right? So first thing I want to talk about in terms of Lewis structures is that it's important that you identify the difference between what we call bonding pairs of electrons to what we call non-bonding or lone pairs of electrons, right? So the practice that we engage in when it comes to representing Lewis structures, and in fact, when representing the bonds, is that we use lines to represent bonding pairs. And we can also use lines to represent non-bonding pairs, right? So the bonding pairs, of course, are the electrons that are being shared between the atoms. The lone pairs or non-bonding pairs are those pairs that are not involved in bonding and therefore not shared between the atoms, right? So just to use a simple example, the chlorine molecule, right? So when 2 chlorine atoms come together, they form the chlorine molecule where you have 2 electrons being shared between the 2 atoms, right? And as a result of that sharing, each chlorine atom will end up with 8 electrons on their outer shell, right? So that is true for this chlorine atom, and that is true for this chlorine atom, all right? Now, so this is actually one way of representing the Lewis structure of the chlorine molecule, right? Another way of representing it is using this representation right here, where instead of using 2 dots to represent the bonding pairs, we use a line to represent the bonding pairs, all right? And there's yet another way. I don't see this too often in textbooks, but I remember one of my professors back in the day did this, which I prefer to use. Another way of representing this is this. All right? So basically, this is your bonding pair, right? And the lone pairs are these lines here that are not between the chlorine atoms, right? So basically, this here is your lone pair, all right? So as far as I'm concerned, you can use any one of these representations for the Lewis structure for any molecules, right? I personally prefer the middle one. I find it easier to use, but you can use this, you can use that. It doesn't matter to me, all right? Okay, so that's a simple example. We're going to move on to more complex examples. But before we do that, let's look at some other more simple examples. So we're looking now at some elements in period 2, which are nonmetals, which would form bonds with hydrogens to form different compounds. So in the case of carbon bonded to 4 hydrogen atoms, right, this is the Lewis structure here. And the name of this molecule is methane. In the case of ammonia, you have nitrogen with 3 single bonds bonding it to 3 hydrogen atoms, and you have a lone pair here. And then in the case of water, you have 1 bond here, 1 bond here, 2 lone pairs here. And then in the case of hydrogen fluoride, you have 1 bonding pair here and 3 lone pairs around the fluorine atom. So these are just basically some examples of Lewis structures. Now, please note, when it comes to drawing Lewis structures, couple of things we need to talk about. One of them is that when it comes to Lewis structures, we're not concerned with the shapes, right? We'll be concerned with shapes later on, right? But for now, when it comes to Lewis structures, we're not concerned with the three-dimensional shapes of the molecules. The only thing we're concerned about when it comes to drawing Lewis structures is how the atoms are connected to each other and the bonding pairs and lone pairs, and that's it, right? So we're not concerned with the three-dimensional shapes, even though those are important, but not important when it comes to Lewis structures, right? You can also, as stated here, the Lewis structure for water may be drawn with all three atoms in a line. Again, we're not concerned with that shape. So you can draw it like this, but you can also draw it like this, right? That's also a legitimate Lewis structure for water, right? So again, this is just underscoring the fact that we're not concerned about the shapes of molecules when it comes to Lewis structures. We're going to look at how we can predict the shapes in the next chapter, all right?
When you get to doing the shapes like the tetrahedral. And,
Right, exactly. Tetrahedral, bent, and so on.
Are we going to have like when the test, I guess, for that comes, whenever we're tested on that, are we going to have it? Because my intro to chem class, we had a chart for it.
Oh, you need a chart?
Or we have to memorize it?
I'll have to think about that one. I'll have to think about that one. But there is a website which allows you to play with these things and you can see the shapes and so on, and that should help you to memorize. But I'll let you guys know when we get to that stage. All right.
The final, right?
Yeah, definitely. Yeah. Okay. Now, there are some instances where you can have what we call multiple covalent bonds, right? So all the examples that we have looked at so far, you have only one pair of electrons being shared between two atoms. But you can also have a situation where you can have, for example, two pairs of electrons being shared between two atoms. And that is illustrated in the case of carbon dioxide right here, where between each carbon atom, or I should say between the carbon atom and each oxygen atom, you have two pairs of electrons being shared here and being shared here, right? So we call this a double bond, right? Each bond represents a pair of electrons, and there are two pairs of electrons here, two pairs of electrons here. And also you can have a triple bond, such as in the case of the nitrogen molecule, right? Where you have three pairs of electrons shared between the two nitrogen atoms, all right? In each case, the atom or the atoms involved end up with an octet. So if you look at, for example, the carbon atom here, it has 2, 4, 6, 8 electrons. In the case of each oxygen, there are 2, 4, 6, 8 electrons. And in the case of each nitrogen atoms, there are 2, 4, 6, 8 electrons, all right? And in fact, you can have also quadruple bonds, but we won't get into that, right? So for our purposes, our limit in terms of multiplicity of bonds would be triple bonds, all right? Okay, so again, in some Lewis structures, you're going to see, in this chapter, you're going to see examples of double and triple bonds present, all right? Now, here's one situation where even though the Lewis structure for a particular molecule is very useful, it has been shown to be not an accurate representation of what is happening. And the example we're looking at here is oxygen. Now, based on the Lewis structure for oxygen, right, you'd think that, okay, all the electrons are paired up based on this Lewis structure right here, right? We now know that that is not true because oxygen is paramagnetic. If you remember, we talked about this before. If we say that a structure is paramagnetic, it means that it has unpaired electrons, right? And the fact that oxygen is paramagnetic can be demonstrated because if you take liquid oxygen and pour it between the poles of two magnets, one the North Pole and one the South Pole, then the oxygen will be held up between the two and form a little bridge, right? And that shows you that the oxygen is attracted to the poles of the magnet, which means that it is paramagnetic, which means that it has unpaired electrons. So therefore, this is not a true representation of the electron arrangement in the case of oxygen. It's more likely to be something like this, where you have these electrons here are unpaired, all right? That's more likely to be true in terms of how the electrons are arranged in the case of oxygen, all right? So this is just an example where you might have something which works well, a model which works well in theory, but when you test it using an experiment, you find that it's not entirely true, all right? Okay, now we're going to get into how do we write down Lewis structures based on molecular formulas that you're given, right? And this applies to molecules and polyatomic ions, right? So let's go through these rules. The first rule is that you establish a skeletal structure that shows the arrangement of the atoms. Usually, well, not usually, in all cases, hydrogens are terminal atoms. What does that mean? That means that hydrogen atoms are not bonded to more than one atom, right? So once hydrogen is bonded to one atom, it cannot be bonded to another atom, all right? The central atom of the structure usually is the one with the lowest electronegativity, all right? And of course, you'll have the table with the electronegativity values of the different atoms so you can establish which one would be the central one. When it comes to oxyacids, meaning acids which contains oxygen, right? What you'll find is that the hydrogen atoms are usually bonded to oxygen atoms, all right? So that is a kind of particular rule specific to oxyacids. The next rule is that when it comes to molecules and polyatomic ions, we try to have the structure being compact and symmetrical, all right? So for example, if you're asked to write down the formula for, let's say, or not the formula, the structure for, let's say, sulfur trioxide, then you wouldn't do it like this, right? You would it would be more arranged like this, right? Where it's more compact, more symmetrical, and not elongated like in this case right here, all right? Okay, some other things we need to, okay, so let's go through the stepwise rules for drawing the Lewis structure of a molecule or polyatomic ion. What time is it, by the way? Okay. All right. The first step is that we need to determine the number of valence electrons. That's very easy. All we have to do is go to the periodic table and look for the group numbers and add them up according to the formula. All right. Step 2, draw a plausible skeletal structure and connect them with single bonds or single dashes. All right. So you need to keep an electron count while you're doing this. Step number 3, place pairs of electrons as lone pairs around the terminal atoms to give each terminal atom an octet, with the exception of hydrogen. Again, because hydrogen cannot have more than 2 electrons on its outer shell. The fourth step is that you assign any remaining electrons as lone pairs around the central atom. And then the fifth step is, if necessary, move one or more lone pairs of electrons from a terminal atom to form a multiple bond to the central atom. I'm going to say some more things about step number 5 because that itself involves a couple of steps which I need to go through with you guys. Okay, so what I'm going to do now is, go through these examples here. And the first example is nitrogen trifluoride. Okay, so the question is, what is draw the Lewis structure of this particular molecule. Okay, so the first step is that we consult the periodic table and we look up the group numbers because that represents a number of valence electrons, right? So in the case of nitrogen, if you look it up, it's in group 5A, so that will contribute 5 valence electrons. And if you look up fluorine, you see it's in group 7, but because there are 3 of them, we have to multiply that by 3, so that gives you a total of 21, and then you add them up. 21 plus 5 gives you 26 electrons. Now, what I like to do is that I like to express this as pairs of electrons. So 26 electrons will be the same thing as 13 pairs, right? So now that we have established the number of pairs of electrons that we need to assign, the next thing now we need to do is arrange the atoms to get the general structure. So as we said before, the less electronegative atom is usually in the center, and then we surround it with the other atoms, which would be the fluorine atoms, all right? And again, it doesn't matter how you arrange them because we're not interested in the shape, all right? So we have 13 pairs of electrons to assign. So we put 1 pair here, 2nd pair here, 3rd pair here, all right? Then the next pair will go on the peripheral atoms, right? The atoms that are bonded to the nitrogen, right? So we have assigned 3 pairs so far. So the next pair would go here. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have used up 12 of the 13 pairs, right? So the next step is, where will the 13th pair go? And the answer is, it will go on the nitrogen atom. And that would be the Lewis structure of nitrogen trifluoride. All right? Any questions about this one? Any questions? Any questions? Any questions out there in Zoom?
Thinking of it as 13 pairs helped a lot.
Hmm?
Thinking of it as, instead of 26 electrons, thinking of it as
Yes,
13 pairs.
that's the reason why I like it, because that's the reason why I like it, because you're assigning pairs. So once you get the total number of electrons, then you just break it down into pairs and then you just assign it accordingly. Okay, let me clear this because there's another example. Going back to the PowerPoint, what's the next one? Okay, sulfur dichloride. So let me go back to this. SCl2, right? So again, we do a total count of the valence electrons. So sulfur, if you look it up, will contribute 6. Chlorine, if you look it up, contributes 7, and there are 2 of them, so that's 14. So when we add them up, you get 20 electrons, which will be equal to 10 pairs. And then we put the sulfur in the middle, surrounded with the chlorines. So we put 1, 2, those are the bonding pairs. Then we put 3, 4, 5, 6, 7, 8, right? And then we have 2 pairs remaining, 9, 10, and that's it. And that would be the Lewis structure for sulfur dichloride. All right? Any questions about this one? Any questions? All right, so what's the next one? SiCl4. Okay, now let's see if you can do this one with minimal help from yours truly. SiCl4. So what's the first step? Based on the previous 2 examples, what's the first step?
So it would be a skeletal structure first, which is going to be, or count the valence electrons.
So silicon. Okay, yeah, you need your periodic table in order to do this. Okay, so silicon will contribute 4. What about chlorine?
7.
7, but there are 4 of them, right? So that's 28. So this will be equal to 32 pairs, which will be equal to, 32 electrons, my bad, which will be equal to 16 pairs. So we put the silicon in the middle and surround it with the chlorines. And then what do we do next?
Connect them all with single bonds.
Okay, so 1, 2, 3, 4, right? So we have used 4 of the 16 pairs. What next?
So silicon has that noble gas configuration, so you'd add pairs to the chlorine.
Okay, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, and that's it. We have used up all the pairs. And therefore, that would be the final answer for the Lewis structure of silicon tetrachloride. Okay, any questions about this? Any questions? Any questions? All right, let me see what's next in the PowerPoint. Okay, formal charge. Very important, especially when it comes to multiple bonding. What do we mean by formal charge? The formal charge of an atom, and this could be in a molecule or ion, whatever, is a difference between the number of valence electrons in a free uncombined atom and the number of electrons assigned to that atom when bonded to other atoms in a Lewis structure. Right? Now, please note that the formal charge is a purely, well, not always, but in some cases, a purely hypothetical quantity and a useful tool. In other words, in some cases, the formal charge doesn't exist in the actual structure, but we use it in order to determine what the actual structure is, all right? Usually, the most plausible Lewis structures is one with no formal charges. So we try to make sure that there are no formal charges. However, you cannot avoid that in some cases, right? When formal charges are required, they should be as small as possible, and negative formal charges should appear on the most electronegative atoms. And then finally here it says atoms that are adjacent to each other in the structure should not carry formal charges of the same sign, all right? Now, there's a formula that I use to calculate the formal charge, right? And you might see it expressed differently in different textbooks. So this is the formula that I use. You may want to write this down. And that is the formal charge. I hate red ink. Okay, so this is my formula. The formal charge is equal to the group number of that atom minus half the number of bonding electrons minus the number of non-bonding electrons. All right? Now, in different textbooks, you might see something expressed differently, but basically, it calculates the same quantity for the formal charge, all right? But this is my favorite way of doing it. It's a group number minus half the number of bonding electrons minus the number of non-bonding electrons. And whenever you're asked to determine the Lewis structure of any molecule or ion, you need to calculate the formal charge, all right? Now, I did not do that in the previous examples because I knew that the formal charges in all those examples are 0. Let me show you how to apply that formula to one of the examples that we just did. So this was, this is the last one that we did, right? If I were to calculate the formal charge of the silicon atom, right, based on the formula that I just gave you, that would be equal to the group number of silicon, which is 4, right, minus half the number of bonding electrons. Now, for the silicon atom here, you have 2, 4, 6, 8 electrons, so half of 8, right? And then the number of non-bonding electrons, there are no non-bonding electrons on the silicon, so that's 0, right? So when you work this out, that turns out to be 0 for the silicon. And if I were to do the same thing for the chlorine, right, what I'm going to do is do the calculation for one chlorine atom because it's going to be the same for all the other chlorine atoms, right? So in the case of chlorine, the group number is 7 minus half the number of bonding electrons. Now, for each chlorine atom, there are 2 bonding electrons. So half of 2 goes here. And then minus the number of non-bonding electrons, which would be 2, 4, 6. And that works out to be 0 as well, right?
For the formula that you're using, couldn't it also just be the group number minus the bonding pairs?
I think so, yeah. Minus half the number of bonding pairs, or minus the number of bonding pairs, minus the number of
non-bonding electrons.
Yeah, that's another way of doing it too, yeah. Whichever way works for you, I don't mind, as long as the answer is correct, right? So as we see here in this example, the formal charges of all the atoms are 0, which means that the entire molecule is 0 in terms of its charge, right? But that's not going to be true in all cases, as you're going to see shortly, all right? In fact, let me see here, going back to the PowerPoint. Okay, here are some good examples, right? Again, you're asked to determine the Lewis structures for these molecules, right? So the first one is COCl2. I don't remember the name of that compound. Let me delete it here. Okay, so COCl2, all right? So you're asked to determine the Lewis structure of this molecule. So we start, just like we did before, we count out the valence electrons, right? So carbon will contribute 4, oxygen will contribute 6, and we have chlorine, which contribute 7 times 2, which is 14, right? And then we add them up. So that's 10 plus 14, that's 24 electrons, which will be equal to 12 pairs, right? So what do we do next? we put the carbon in the middle because it's the least electronegative of these elements, and we surround it with 1 oxygen and 2 chlorines, all right? And then what we do next is put the bonding pairs. 1, 2, 3. Then we put the non-bonding pairs. 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have used up all the pairs, right? So the next step that you should perform is determine the formal charges of each atom, right? So we do that for the carbon. So according to the formula that I use, it's a group number, which is 4, minus half the number of bonding electron, which is 246, minus the number of non-bonding electron, which would be 0. So that would be 4 minus 3, that would be plus 1. In the case of oxygen, that would be the group number, which is 6, minus half the number of bonding electron, which is 2, minus the number of non-bonding electron, which is 6. And according to my calculation, that's equal to minus 1, right? And then finally, in the case of chlorine, so again, the same calculation would apply to each of these. I'm just going to do the calculation once. So that's 7 minus half of 2, which is the bonding pairs, minus 246 electrons. And according to my calculation, that is equal to 0, right? So the chlorines will have no charge on them, but the oxygen will have a minus 1 charge, and the carbon will have a plus 1 charge. Now, when you have a situation like this, where one atom is negatively charged and it's bonded to another atom which is positively charged, you can have this happening, where this pair of electrons here will come down here, right, to form an extra bond. So when this pair of electrons come down here to form an extra bond, that negative charge here will cancel out this plus charge. So your final answer, I'm going to draw down here, would be Cl, C double bond O with 2 lone pairs, single bond Cl with 3 lone pairs, and this would be the final answer right here. All right? So that's where formal charges become important, because as a result of the formal charges that you'll end up with these 2 atoms bonded to each other, you can have the formation of multiple bonding, where this pair of electrons come down to form a second bond, and therefore you end up with a double bond between the carbon and the oxygen. And that's it. All right? Okay. Any questions concerning this example? How about you guys out there in Zoom? Any questions? Any questions? Okay. So let me go back to the PowerPoint to see what the other example is. Okay, the other example is SO2. So I take it it's okay for me to clear this. So let me delete all this here. Oops. Okay, so SO2, okay? All right, so what's the first step? Let me hear what you guys have to say. What's the first step? Okay, so sulfur is what? Sulfur is 6. Oxygen is what? Multiply by 2, so that's 12. So the total number of electrons here will be 18 electrons, which will be equal to 9 pairs, right? So we put the sulfur in the middle, surrounded with the oxygens, and then what?
We start with us, yeah.
Bonding pairs first, right? 1, 2, then
And we fill out the valence.
3, 4, 5, 6, 7, 8. All right? Next step would be to calculate the formal charges, right? So let's deal with the oxygen first. How would you calculate the formal charge of the oxygen? That would be equal to what?
Why are there only 8
Yeah,
pairs?
there's only 8 pairs.
I'm sorry?
There's only 8 pairs. We need 1
Oh, one more. I'm sorry. Yeah, one more here. That goes on the sulfur. Thank you for pointing that out. Yes. So formal charge of oxygen. How would you calculate that?
It's going to be 6
6 minus
minus the bonding pairs, so 1,
half of 2,
2.
or 1. Yeah, 1. And then minus
the non-bonding pairs, or non-bonding electrons, which would be
6, right? So this works out to be minus 1. So that means each oxygen would have a -1 charge, right? And then we do a similar calculation for sulfur, all right? So that would be equal to what? How would we calculate the formal charge of sulfur?
So it'll be 6
Mm-hmm.
minus 1/2 of 4
Mm-hmm.
minus 2.
Mm-hmm. So that's 6 minus 2 minus 2, that gives you what? Plus 2, all right? So each oxygen has a -1 charge, and the sulfur in the middle has a +2 charge. So what do you think is going to happen next, based on what we did in the previous example?
We have a
What do you
quorum.
think?
It just kind of happened.
Emily is
You
unmuted.
look like
Oh,
you're mixing.
Emily, could you mute your mic, please? I'm hearing a lot of noise.
So with this, will we end up doing double bonds in between the?
Exactly.
Okay.
You're going to have one pair of electrons going here. So when this pair of electrons goes here, this negative charge cancels out one of the 2 plus charges. And when this negative charge goes here, this negative charge will cancel out the other plus charge. So you're going to end up with O, double bond, S, and then a lone pair here, double bond O, and then 2 lone pairs, and that's it. And this here would be the final answer. All right? And that's how you do that. Okay, any questions about this one? Any questions? All right, I'm going to stop here because it's now almost 12:30. What you can do is try the third example, right? And then we can get together and talk about that. Since I did not remember to bring copies of assignment number 9, what I'm going to do is publish it so that you can have it to look at between now and next class. Let me do a quick view of this here. Okay. All right, so okay, unfortunately, these questions are not in the order that I would prefer it to be because, for example, you won't be able to do questions 1 or 2 or, hold on, and then, hold on, let me see here. And the numbering system is messed up also. I may have to go back and change this, but I'll just publish this for you guys to look at. You won't be able to do this one either, nor that one. No, this one you should be able to do. This is a Born-Haber cycle question. So you can use what we did, the example that we looked at in order to answer this. And also, I need to change this here because of the definition that we talked about in terms of the lattice energy. This arrow should be pointing in the other direction. Okay. So you can look at this in the meantime. I'm going to make some changes and re-upload the modified assignment number 9, and I'm going to make sure that I'll bring that to class so that we can look at those problems together. All right? Okay, let me just get those persons who came in late before I leave. Let me see here. Barner, is Barner here? Okay, I don't see Barner. Davis. Okay, I see Davis. Hernandez is here. Jernigan. Is Jernigan here? I don't see Jernigan. Fan. No, hold on, wait a minute. Not Fan. Osorio. Osorio is here. Ranley. Is Ranley here? Yes, Ranley is here. Wilbert is here. And Zaradka is here. Okay, so that's it. So I'll see you guys on Wednesday. Oh, also, I don't know if I told you guys this before, Your next test would be in a week. All right, so did I post that in the announcement? If I haven't, I'm going to make sure I post it. Just to remind you, all right? And that test will cover, oops. That test will cover chapters
4 through 7, 4 through 6.
6, 7, and 8.
What about 4 and 5?
No, that was chapter 2, right?
Oh, yeah, you're right.
I mean, that was test
Yeah,
2.
okay. I forgot about that.
Right. So 6, 7, and 8, right? So what we're doing now will not be covered in that test. 8, 7, and 6, the previous chapters will be on that test.
And that's our final exam, right?
No, the final exam is after that. And I need to post the date for that as well. Keep forgetting to inform you guys about those things. So,
Are we gonna do a like a study guide before the test that covers everything, or
well, that's the reason why I required the assignments to be done by certain deadline times. By the way, did I send back you? I sent back to you guys assignment number
you sent back the test too? Yeah.
test 2, but in terms of assignment, I'll have to have it saved on my thumb drive. I need to, if I haven't done so already, I need to send back to you your graded assignment number 8. Hold on.
Last one we got was 7.
We did.
You submitted 8, I
Right.
think, right? Hold
Was
on,
it
let me
8?
check something
Yeah.
here. Okay, so I haven't graded 8 yet. So far, I see 4 assignment 8 submitted. So if you have not submitted, oh, the deadline is tonight. Okay, good. So I need to grade that and get that back to you so that you can have that to help you to review for your final exam. But I'm quite sure I sent back the others, 6 and 7 to you guys. So make sure you review those. I'll make sure grade that and send it back to you as well so that you'll be prepared for test number 3.
And then, Professor, when you get a moment, are you able to upload that PowerPoint to the website?
Let me see here.
No, I forgot to email you about my test 1 grade. I'll email you that.
Yeah,
today.
because I plan to grade that today.
Do you still want me to email you?
Yeah, just remind me because I have several things on my plate right now.
All right.
Yeah, so yeah, do that as soon as you can.
Mhm.
Okay, so you're saying that I should publish PowerPoint and chapter, oh, it's there already. Oh, 9, sorry. 9, my bad.
Oh, thank you.
Okay, so it's published.
Awesome. Thank you.
All right.
You have a good weekend.
Yeah, you too. Take care. And for you guys out there in Zoom, I'm going to exit now. You guys next Wednesday. Oh, wait a minute. I see 2 chat. Oh, okay. So to answer your question, Miss Afra, I'm going to do that today. I don't know if I've done it already, but I'm going to upload some past test questions based on the topics chapters in chapters 6, 7, and 8. All right. So that's yet another thing I need to remember to do. All right. So you can email me just to remind me because, of course, knowing me, I'll forget something. So hopefully I won't forget that. But yeah, email me to remind me to upload a past test. All right. Okay. If there are no other questions, I'm signing off now. So I'll see you guys on Wednesday. And I'll be here in my office hours from 2 to 5 if you have any further questions. All right. All right. Take care.